Sorry?
Is a Templeton Foundation?
Yes, we will talk about politics, actually.
No, religion,
Yeah, right. Okay, thank you very much for the invitation. I'll talk about basically non-commutative surfaces. I decided to orient a little bit my talk today because of Masoud's talk this morning. I was talking about the interest of finding curved non-commutative spaces, so I think it's a good occasion to talk about that. And indeed, I used twist method for that, so this will be an application of a method regarding twist that I designed a few years ago, that I'm designing for a few years now. So the first example of a non-commutative surface is for sure the non-commutative torus. So here you have a torus. Right. So so it has a lot of structure. It's a group. It's a Lie group. It's a torus. It's a Lie group. It's also a R2 homogeneous space. It's a Kähler flat manifold. Okay. A lot of things. Okay, very, very simple. But basically, I mean, it's very, very simple examples, right? So, yeah, it's yeah, yeah, it's even a abelian Lie group. Okay. So now, okay. So how do you get or do you pass from this commutative torus to the non-commutative torus? For example, you can use Fourier theory as you described, for example, but you can use also Rieffel deformation quantization scheme using Moyal twists. So this means the following. You have an action. Okay, this is an R2 homogeneous space. Okay, so it acts on the so R2 acts on the functions on this space. So let's say the C star algebra of continuous functions on the torus. So let's call this action alpha. It's an action by automorphisms of C star algebra. And it is it's a strongly continuous action. Isometrical for the C star norm, of course. And by strongly continuous, I mean a condition, a property that implies that the space of smooth vectors for R2 are actually dense in the C star algebra. So density of smooth vectors of alpha in CT2. So let me call these smooth vectors CT2 infinity. Okay, so there is somewhere a smooth and a subalgebra of smooth functions. Okay, and then you can produce the field of continuous field of deformation field of C star algebra simply by writing the following Moyal formula, if you want. So if A and B are elements in the smooth vectors here, then you can look at the function here. Where x and y are elements in R2. Okay? So that is a function that is defined on 2 points of R2, so from R2 cross R2, and valued in the C star algebra, or actually more than that, valued actually in the smooth vectors. You weight this by a, let me write this. You weight this by a phase, a pure phase. So theta here is a, let's say, real number that is not 0 at the moment. Okay. And this is the dot product in R2. And this J here is just a complex structure. On R2. And that is now an oscillating function in 2 points valued in the smooth vectors. And due to the fact that it is oscillating, you can actually integrate it as a oscillatory integral. And that is another description of the torus that you gave. Let me put a 0 here because there is no curvature. Not yet. Okay. So the result of Rieffel, maybe let me write it here. The result of Rieffel is that this product actually closes on the smooth vectors as an associative algebra structure. Which is actually pre-C star. So you can complete that with respect to a C star norm that depends on theta, C star completion, and that is the non-commutative torus. And the field here is actually smooth in theta and restricted to the smooth vectors. It's a smooth deformation in theta. And at the level of the C star completion, this is a continuous field of C star algebras. So that is the non-commutative torus. And so the question is, so the question that you were talking about, one question that is about you were talking about. Yes, in this case, yes. Yes. Yeah, yeah. In this case, yes. In this case, yes. But it could act. Yeah, yeah, yeah. But it. Yeah. Exactly, it's commutative, so you can actually commute the infinity and the T2. No, but actually, if you have an action, you can replace. What I mean here is that you can replace actually this C star algebra by any C star algebra on which R2 would act on that way, and then you. Okay, so the question is, maybe before the question, the nice features that you have here is certainly smoothness. Yeah, you have smoothness for sure. Smoothness in many ways, smoothness of the smooth elements that are closed under the deformed product, and also smoothness of the deformation field in the parameter. Okay, so that is a very good thing. You have derivations also because of smoothness in some sense. Okay, so the delta 1 and the delta 2 you were talking about, and you have coming from the flat K-lot geometry, you have all these features that comes in using the twist deformation. Okay, so also complex structures. something else. You have a trace that is important also. So in your setting, this is just the first. The trace is just the first element in the series, and in that setting, it just corresponds to the integration on the torus. Okay. So in that context, this is the trace that you have. Okay. So the question now is it possible to find an analog in a higher genera, higher genus? And analog, by analog, I really mean an analog with these nice features, of course. Okay. So there were several attempts to that, several notions of a non-commutative Riemann surfaces in the literature, but as far as I know, none of them has these smoothness properties. Even the trace is extremely hard to deal with. So in literature, but smoothness is still a problem. Still a question. Okay. Candidate for that? Yes, this is the subject of my talk. So, vector fields, for example. That they do not come from a group action like this, but yes, vector fields, for example. Yeah, but this, okay, that's a good question. And okay, I answer a bad answer, vector fields. But then maybe later you will be more satisfied with my answer. Okay, so if I take a genus 2, then I have a Riemann surface sigma G, that is genus G Riemann surface, compact, orientable. Manifold or surface. And so there are, it's a very good manifold. It's a Kähler manifold in general. Okay, you can always find a Kähler metric with a constant negative curvature on it. That's very nice, but there is of course difficulty, which is that when G is greater than 2, this space is not homogeneous anymore. So it's not homogeneous for any action of any Lie group on that. And it's, yeah, okay. But at least there is one good news, which is uniformization theorem. Is that if you look at the hyperbolic plane, D that maybe you realize abstractly as SL2 of R over SO2. Okay, so SL2 of R acts on the Poincaré disk with an isotropy fixed point that is SO2. So you have an identification with the hyperbolic plane with its geometry with this coset space. And then you can always find a discrete subgroup gamma of SL2 of R that acts on isometries, by isometries on the hyperbolic plane. Okay, so this is basically, well, maybe with a P here, this is basically the isometry group, okay, of D. So there is a discrete subgroup here, which is the Fuchsian subgroup. That realizes after quotient, so there is still an action of SL2 of R by isometries on D, and then you can look at the quotient by this left action, and that is a realization of the surface. Yeah, but then don't forget, you want to have all these very nice features that gets you very close to just a manifold. Okay, so as soon as you start taking cross products and everything, no. And the smoothness also is difficult to reach. So yeah, you can do that, but that's not what I'm suggesting here. So, so it's not a homogeneous space, but still, it's a quotient of this hyperbolic plane. So the hyperbolic plane is not a group either, like it was in the torus. It's not a group either, but it's almost a group. It's a symmetric space. It's a Hermitian symmetric space, non-compact type. The first example, interesting example of a Hermitian symmetric space that is not flat. So it's a symmetric space. D is not a group. D is not a group. Well, not as such, but it's a symmetric space. So it means that if you look at this space as a scalar manifold with its metric, and if you take a point here in the space, then you have a local geodesic flip. Okay, so you have a centered geodesic flip symmetry at X, okay, in this space. And it turns out, and that is the definition of what is a symmetric space, which is that for all X, this symmetry actually extends as a global transformation of the whole disk, which is actually an isometry. Well, let me put a P to be really correct. So that's what you have. That's a symmetric space, Riemannian manifold, such that the centered geodesic symmetries that always exist on the manifold actually extend globally to the space as isometries of the space. So that's very usual definition. So now you can start thinking about a strategy to define non-commutative surface, deform this guy in a way that you would get a deformation that would be PSL2 of R equivariant, and then get down the star product, the non-formal star product you would have here, get it down to the gamma action on the surface. Okay. So concerning these deformations, PSL2 of R deformations of the hyperbolic plane, there is a conjecture due to Alan Weinstein in '94. Which is as follows. Suppose that you have a star product. You have a star product on the space. Okay, so suppose that for all, let's say, U and V compactly supported functions on D, okay, you have a formula. Suppose that you have a formula. Let me write this. Okay. Suppose that you can write some type of integral of this form. So A is some amplitude function of 3 points, and you integrate over D cross D, something that is very similar to the formula that is here. Okay. And then you have some phase function S there, and you integrate in U in over U and V in Y and Z coordinates with respect, for example, to the UV measure you have on the scalar manifold, the symplectic manifold. So this is the formula you write, and assume that this formula extends, let's say, formally to the space of smooth functions power series in theta. Theta is a formal parameter, let's say, in this formula. Okay, extends to this as an associative a product law with a semi-classical condition, so such that, let's say, when theta tends to 0, then this product would behave that way. Okay, and this is the Poisson structure associated to the symplectic Kähler form that you have on the hyperbolic plane. Okay, so assume that you are in this situation, then the conjecture by Weinstein is that nothing is known concerning the amplitude A here, but it says something about the phase. Okay, so the phase is constrained. Then the phase is the flux of the symplectic structure, the Kähler 2 form, through the triangle, through a certain geodesic triangle. Exactly. That's the exactly. This is the hyperbolic area of a certain triangle. And let me call this triangle phi of x, y, z. Maybe I should use this thing. Otherwise, after a few blackboard, we won't see anything anymore. So let me write, what is this triangle phi? I guess there should be something to... okay, great. So the triangle there is not the geodesic triangle with vertices x, y, and z. Not exactly. It's a little bit more complicated triangle. And one thing which is even more complicated in this conjecture by Weinstein is that in general, for 3 given points in the hyperbolic plane, this triangle does not exist. But okay. So this triangle phi of x, y, z is constructed that way. You take, let's say, 3 points like this, okay? And then you construct a triangle of that form, geodesic triangle, like this, okay? Which admits x, y, and z as midpoints of the edges. Okay. So for example, if you look at the disk model, and if you take an extreme triangle like this, okay, you see that these points here play the role of x, y, and z, and there is no triangle because these points are not defined there. Okay, And that is the limit situation. And if you take your points even more apart than these ones, then you don't have a triangle. Okay, but as soon as x, y, and z are close enough to one another, then you can integrate the symplectic structure, and that is this space S conjecturally. Okay, so
it's doubling distance in the non-commutative space too, right? You put the phase.
Right. Yeah, right. But there, the triangle is defined. Yeah, then it's fine. Okay, but here it's only local. So let me call phi. Okay, let me call phi this map from D3, which is only local, right? Because of what I said, D cross D cross D to itself. Okay, and that sends these points x, y, and z on these points. So this is psi. Okay, and if you think about it, then this sz of psi here, sx and sy is actually psi. So it's a fixed point for this isometry here. Okay, so let me denote this map by phi, and okay, with this property of fixed point. And what I just said is that this phi is generally not well defined on the whole hyperbolic plane. So now the idea is a little bit more precise than what I said. So the idea to get these surfaces is to solve this conjecture first. That when you have a product like this, oh, I forgot to say something very important, but that is, okay, that was underlying there, but of course you have SL2R invariance of the product, of course. So if you have a star product under that oscillatory integral form, that is SL2R in equivariant, then, well, we don't know anything about the amplitude, but you know conjecturally you know something about the phase. That should be the flux of the symplectic structure. So first solve the conjecture, if possible. Second, find an amplitude A such that this a priori formal expression would close on some subspace of functions, possibly smooth, on the hyperbolic plane, such that star theta closes on some function. So, not power series, right? Formal power series. Genuine function. Okay, so not formal power series. On some function subspace, subalgebra, maybe subspace, on V, that would be very nice already, but you have even more, one more constraint, that is that this function subspace, so let me call it A, for example, this function subspace should contain the gamma invariant, so the gamma periodic functions. Otherwise, you cannot go down. So in general, what is constructed is some kind of Schwarz spaces. You have functions like this, but we need much more, of course. We need all the gamma invariants under the Fuchs group actions. We need all the gamma invariant functions. Okay, so on some subspace of functions, A that would contain the gamma invariant functions. Okay. So where? Yes. It's Yeah, the analog is here. You see when theta goes to 0, okay, then this product would tend to the commutative product at 0th order term, and then at first order term basically to the Poisson structure. That is what you have in the Moyal case. For example, if you write this, so I wrote this, right? That's what I wrote, I think. I put the j here, but doesn't matter. And then 1 over theta square, dx dy. Yes, because I should divide by theta here. That's why. Thank you very much. Thank you. It's a division. Absolutely. You're right. Absolutely. Yeah. Okay. So that is the yeah. Basically, you change the coordinate. Okay. You put z equal 1 over theta gx, and then the Jacobian gives you this guy, and then you get the formula for the when theta goes to 0, you get so here you get a theta and not a 1 over theta, and then when theta goes to 0, this becomes a constant. It goes here, and you get the delta Dirac delta distribution formula, and that's why you have this term here in a times b. That's the reason. But you're totally right. I should write 1 over theta. Okay. So. The remark here is that this, suppose it exists, suppose that you can actually solve this conjecture, and suppose you find a product like this, then this thing yields a Drinfel'd twist. A Drinfel'd twist for actions of ax plus b. So let me explain that. Well, because the conjecture says that any time you have a product like this, and this is what you're looking for, this is true. So if you find one, in particular, you solve the conjecture. Yeah. Yeah. Yeah, it's a question. Yes, yes, it is possible. Yes, yes, yes. But, I cannot tell you right now, otherwise there is no suspense anymore. There's a matter of time also, that's true. Okay, so what do I mean by this? I mean that, okay, let's look at this formula. Okay, suppose that you have, so first, let us observe that D is actually, it's not a Lie group, but it carries a group structure, which is the ax plus b, because this is, so let me call B the Borel subgroup of SL2R. Okay, so it means that B is simply the group, for example, realized by triangular matrices of that form, where A and N are real numbers. Okay, so these are like this. And this identification here is clear because of Iwasawa decomposition. So you have that SL2 of R is actually, as a manifold, it's actually the product of B and the group SO2, which is precisely the stabilizer group that gives you D. So you have an identification between D and B, simply that sends an element G in the group over its action on the base point, which is SO2 in this case. So this is really an identification here Okay, and now if you restrict this formula that I wrote there to this formula that I wrote there to under the form of a twist for B. Okay, so if you have an action alpha of B over an algebra like this could be, for example, this one. Okay. Then you can write this. This is the unit element in B. So you view B and D as identified through this map, right? And you can write this. And simply evaluate the functions A and S in 3 arguments on 2 arguments simply by putting the unit element of the group here as a 3rd element and write this formula. And formally, it's not difficult to see that if this is associative, this is a universal deformation formula. This is a Drinfel'd twist for actions of B over any associative algebra. Okay, so this gives you, at least formally, okay, this gives you a formal Drinfel'd twist. Drinfel'd twist. And so you have, what you are dealing with is a problem in the space of Drinfel'd twist for AX plus B. Okay, you look at the space, maybe this space has some structure, okay. It's an infinite dimensional space, possibly. Actually it is. But it has a structure, and you are looking to a problem in that context. So what is this problem? Yeah. So if you have a twist like this, okay, let me say that you have a, let's say, star theta, a Drinfel'd twist under this form, okay, for AX plus B. You can look at the space of these. Okay. And for each such thing there, you have a group that is attached to that. Okay. You have the group of the twist, okay, which is simply the group of diffeomorphisms of the group B itself, which is AX plus B, this group there, okay, which preserve the star product, the twist. And what we want, if you think about it, what we want a group that is the group that I called the internal symmetry group of the twist. Okay, and what we want is to find a twist such that this internal symmetry group could contain SL2 of R with its action on B that is given by this hyperbolic action. Okay, so that is what we want. So the idea is to start from twists that do not satisfy this thing. Okay, we start from twists that do not satisfy this thing. But since they are Drinfel'd twist on AX plus B, they already satisfy the AX plus B equivariance. And we want now to pass to a group that not only contains, so this certainly always contains AX plus B equivariance, but maybe sometimes it doesn't contain the SO2, extra SO2 invariance that I have in the SL2R action. Okay? So the strategy is to start from a non-twist to a non-twist star theta, okay? So for B, okay? And so on this space of Drinfel'd Twist, you have the group of equivalents of star product that act. Okay, so you start with such an equivalence that you write like this. For example, if you write it at the level of functions on the group B, okay, you can write something like this. Okay, it must preserve, this is an equivalence that must preserve the B equivariance, so it must be a convolution operator on the group. So of that form, okay. And the idea is to find a U such that starting from a non-twist, you get an internal symmetric group that contains the circle action on the hyperbolic plane. So that is the idea. And actually, you can achieve that by solving an evolution equation. So, yeah, I still have a few minutes. So, the twist, the non-twist that I start with is a twist that I constructed in 2002, I think. That is a very, very well-behaved twist from the point of view of functional analysis. That I don't have time to talk about that, but that's a very good thing. Okay, so in particular, it acts as a twist. It deforms the space B1 of B that are, if you want, the smooth functions on B that are bounded, and all derivative bounded. Derivative, I don't have time to define. Okay. With respect to universal enveloping algebra element of the group here, actually. So it's a very nice space which contains certainly the space of, once you identify D with B, of periodic functions for any arithmetic group action that you have on the hyperbolic plane. So that's a very good thing. But the bad thing is that its internal symmetric group does not contain this rotation group. Okay, so you have to deform it. But this is the one you start with because it has already very good properties. Okay, and the way you deform it is that way. Actually, okay, so the kernel of this, thing, which is it's a distribution on B that is possibly formal already at this level. Okay, hopefully you will get a non-formal solution. That is what it is actually, but at this level it's only formal. And U, so the theorem, if you want, is that U is solution of an evolution equation for an operator that is a second order differential operator. So it's a wave operator. It's a wave operator, absolutely, yeah. Second order. But it's a wave operator on a curved space, on the anti-de Sitter space 2, which is there. There's some kind of a Wick rotation there that I don't understand very well, but it's okay, that's life. Okay, so it's a second order differential operator. Always solution of that. And then you can get the product explicitly because you know the equivalence explicitly, and you can go through all the computation. I don't know if I have time.
Okay, over time, but I believe that we can.
Yeah.
We can use that.
Okay. Great. So maybe 1 minute just for the formula, or 2 minutes just for the formula. Yeah. So in the formula there is a geometrical notion that is is very, very classical in soft symplectic geometry, which is the notion of moment mapping. So there is a moment map there that will play a role. But of course you can compute these moment maps totally explicitly. And also another thing while I am erasing here, is that this method that I wrote you there, this evolution method, okay, I didn't write the operator. It comes from somewhere, works actually for any Hermitian symmetric space of non-compact type. So you can, more or less, you can if you go through, okay, we wrote the operator, so we know that it's going to work. We didn't compute explicitly solutions as we did for the hyperbolic plane, okay? But it works for Hermitian symmetric spaces. So in particular for compact quotient of Hermitian symmetric spaces would work as well, okay? Right. In inverse cancellation, yeah, absolutely, yeah. So moment map. So you have B that is identified with D, and this goes, you have the moment map J that realizes this SL2R symplectic space, homogeneous symplectic space. That's the moment map as a co-adjoint orbit of G, but that is the same as an adjoint orbit, because here you have the killing form that is non-degenerate. So you have an identification between these two spaces as SL2R spaces. And then you end up with a co-adjoint orbit like this. It's actually a Minkowski sphere in this SL2R, right? But that is this one that is touched. And then you take a point here, x, okay, or j of x. Okay, you have this j here. Look at the group, okay? And you look at its tangent space, and you project orthogonally with respect to the killing form on the tangent space. So you get a projection, okay, for all x. There you have a projection from SL2 of R onto the tangent space at points gx of this orbit, okay, that is the beta. Beta is the killing form, beta orthogonal projection. And then you have a map sigma x that goes from B to this space, okay, and which is simply the composition of the moment map and the projection. Okay. So maybe pi of gx. Okay. So sigma of y is simply pi gx, g of y. Okay, so this has already been considered by Weinstein and Chevera, probably Chevera first. Chevera map. Okay, so basically it's the moment mapping, and then the formula is now like this. Okay, so you define a flux. The flux is not exactly as in the not exactly as in the Weinstein conjecture. Actually, Weinstein conjecture is not completely true. It's only true up to semi-classical approximation, but the right formula is this one. So this is the unit element of the group B, and then you just compute some symplectic area inside the cell2 of R algebra, Lie algebra. Okay, so that is S of xy, okay, like this. And then the formula is like this. This is the Jacobian of this map at point X multiplied by the Jacobian of the same map at point Y times a function that I will call E theta evaluated on xy, and then you have the action of the element x and the element y. You integrate that over B cross B, which is the hyperbolic plane, identified with the hyperbolic plane through Iwasawa decomposition. And there is some kind of constant there, and I still have to tell you what is this E function. This E function is the Laplace transform of the first type Bessel function with parameter rho is the scalar curvature of the hyperbolic plane here, so must be maybe like this, theta, okay? And you take the derivative of that. It's a one variable function, complex variable function that you evaluate on the pure imaginary axis, and that is the function E theta of x. Of the Laplace transform, that's the Laplace transform. This is a one variable function, so you have a Laplace transform. Yeah, that's the Laplace transform. So that is Bessel function, and that comes from the solution of my evolution, right? You get these Bessel functions. So that is the first type Bessel function with parameter, the square root of the curvature divided by the deformation parameter, and that is the Laplace transform. And you see this formula is, so that is the twist. This formula is completely explicit, and because of this fact that it is explicit and after all not so bad, I mean just a Bessel function, Laplace transform, and a quite simple transformation in terms of the moment map, you can actually prove the stability of a subspace A that contains the gamma invariant function. And then you have, you can pull it down. Thank you.
Thank you very much. There's still some time for questions.
So presumably Drinfel'd Twist gives a canonical Hausdorff quantization.
No. So no. There is a possibility of still. It's not exactly Fedosov. So the Fedosov star product correspond to one precise Drinfel'd twist, but you still have a degree of freedom there, which is actually a functional degree of freedom. So it's not exactly that. Not exactly that. Almost that. So same type as Fedosov, because there is an invariant connection there. There is an invariant geometry, and it's built up in terms of an invariant geometry. It's correct, but it's not exactly the Fedosov product itself. Because this guy here, because the Fedosov star product is not well behaved regarding this property of functional analysis there. So if you take the Fedosov star product that you run on B, then you end up with possibly, first it's a formal expression, but suppose that you are able to get it non-formal, then you still have to deal with this stability of functions that would contain periodic functions, and that doesn't work actually. For example, for the Jordan twist, that is due to Gerstenhaber and Giacinto, I think, that doesn't work. For that we have proven that there is no B1 stability for this Jordan twist. which is maybe a bad news, I don't know. Or maybe good news. I don't know. Yeah, you get C-star algebra. It's unital at the level of the gamma periodic functions. Yes, because the surface is compact. But the thing is that in the this is unital. Not generally not for the hyperbolic plane. You can for example deform the non-unital C-star algebra of functions that vanish at infinity over there. But for the surface, yes, you get unital. But the problem is that, but it's the same with the torus, is that of course one thing which is not there is Fourier theory, because for a gamma surface there is no Fourier theory corresponds to a number theory that is not exactly simple. Generator and relations, it's hopeless. It's hopeless, but you have, not for C-star algebra, and now we have some work with Radulescu where we prove that there is a von Neumann version of that that gives rise to a type 2-1 factor over there. And that is related very much to the von Neumann algebra of the not amenable group gamma. It's some kind of deformation of this von Neumann algebra. So for under the action of B there, so for this universal twist that is there, the star, okay, not the sharp, but the star. Yes, you're right. For the other one, I don't know. The reason for the invariance of the K theory under deformation there is that basically it's the solvable Lie group action, and you basically look. I mean, from the C-star algebra point of view, you look at the cross products, and then it doesn't change. There, I don't know. I guess yes, is the same, but I don't know. But what is true is that inside, not the K theory, but inside the invariance, not the class of invariance, when inside the cocycles, okay, not the. So, for example, if you look at the cyclic homology version of the K theory, right? You look at the cyclic invariance. They move with theta. The class doesn't move, but they move. And that would be a way maybe to compare between different von Neumann algebras related to gamma. The way they move. And smoothness in theta is very important there, because you can actually take derivative in the cyclic homology, in the cyclic elements. I'm sure yes, but I don't know the answer. I'm sure, yeah. I thought about that, but I don't know yet. But I'm sure. Well, there you have already the curvature that appears, but yeah. But I don't know. I don't know more than that. But certainly, yes, certainly. No, because I think Landstadt and Reburns, this is only for Abelian. So they need yes. No, okay. Okay, no, I think, okay, I think you were talking about Kasprzak, not Abelian. Could be, yeah. Could be. But this is for C-star algebras. Yeah, here is really Frechet, smooth. But maybe at the C-star algebraic level, you're right. Yeah, maybe you're right.
I want to say remarks, but my French is really bad. I have a friend, French, say